But the grains would get everywhere. Oh hi, we were just talking about sandstones. But what is a sandstone? Where is a sandstone? How is a sandstone? Let's find out together. Hi everyone, my name is Dr. Brooke Johnson and I'm a geologist who studies rocks that are billions of years old and the tiny little fossils that we find in those rocks and on them, sometimes under them, and occasionally adjacent to those rocks. This channel is where I talk about all things geology that I think are cool. You can also find me on other social media sites everywhere as Geologist Johnson if you're really that keen to get some extra Geologist Johnson in your life. Why wouldn't you be? Why? You've probably noticed this snazzy Proterozoic Park shirt featuring the Proterozoic eukaryote microfossil to pan your planet. If you want one of your own, links in the description. Money goes back into the channel so I can make it more fun and useful for all of us. Me, you, that person over there, whoever, all welcome. Today we're going to be talking about sandstones, so let's crack on. Sandstone is a common type of sedimentary rock found all over the world throughout most of Earth's history. Sandstones formed and are still forming wherever eroded sedimentary material is being deposited into a basin. Now, in geology, a basin is just a big, relatively low-lying area where sediment can accumulate and be stored for geological timescales. This means that sandstones can form on land, in deserts, lakes, rivers, river flood plains, on the coast where river deltas go into the sea and where currents carry those sediments further along, and even out in the deep ocean. Sandstones deposited by the same processes in the same types of environment usually have the same characteristics, even if they're deposited far apart in both space and time. For example, this sandstone is only 175 million years old and was deposited in a river delta on the edge of the sea in the early Jurassic period. All these dark lumps are bits of plants from the jungles of ancient tropical Yorkshire in northern England, and anyone who's been to Yorkshire in northern England will tell you it's not tropical anymore. This other sandstone was also deposited in a river delta on the edge of the sea, but there are no bits of ancient plants in it. That's because this sandstone is 3.2 billion years old and is from near Barberton in South Africa. So even though there are no plants that far back in time, there were lots of microbes and they glued together the sediment and left these dark, crinkly laminations. So even though these sandstones were formed billions of years apart on completely different continents to the side of the planet from each other, they were formed in the same kind of depositional environment and by the same processes, so they have very similar characteristics. And importantly, they both hold lots of information about the ancient environments they formed in and the life that inhabited those environments, whether it was trees, tiny little bacteria. In this episode, I'm going to give you a quick introduction to sandstones, but first, to truly understand the sandstones, let's first understand the sand. Sandstones are sedimentary rocks, and this means that they're formed from the accumulation of sedimentary grains, either eroded from pre-existing rock or deposited as chemical precipitates on a planetary surface. Sandstones are part of a subgroup of sedimentary rocks called siliciclastic rocks. Now the silici part means made of silica or silicate minerals, like quartz, and the clastic part is a generalised term used to describe the different grains that we would get in that rock. Siliciclastic is often shortened to just clastic, especially when the component clasts may include grains of other mineral types, such as carbonates or phosphate, or even other chunks of eroded rock that haven't been broken down into individual grains yet. And it's these clasts that are the sand that makes up the sandstone and gets into your sandwich when you try to have a picnic on the beach. Clastic rocks are composed of three main components: the framework grains, the matrix, and the cement. The framework grains are the largest clasts in the rock and they provide the overall framework and structure for the rock. See, it's a pretty sensible name for once. The matrix is finer grained material that is deposited at the same time as the framework grains. It might be made of the same material or something completely different. In this example, the framework grains are mostly quartz and some feldspar, and the matrix is this green iron clay. The cement is a fine-grained or even crystalline material that fills remaining space between the framework grains and the matrix, if present. The cement usually forms through the chemical precipitation of minerals during or after burial, and we call those post-burial processes diagenesis. Sounds pretty grand when you say it like that, doesn't it? Cements can be derived from the framework grains. For example, in many quartz sandstones, the pressure of burial causes some of the quartz to dissolve and then reprecipitate as cements gluing it together. Or it can be a completely different kind of minerals, such as carbonates or sulfides, that infiltrate later on. In this Mesoproterozoic example, the quartz, feldspar and glauconite framework grains, and the glauconite is those green ones, are cemented by the carbonate mineral calcite, which is these rhombus-shaped crystals that you can see all over. The absence of a matrix or cement is also important to take note of, and that may provide you with extra information about the depositional environment or the processes that have happened to the rock after burial. For example, sandstones deposited in deserts or on beaches may not have any matrix, and they may end up getting completely cemented solid. On the other hand, some desert sandstones or beach sandstones may lack any kind of significant matrix or cement, and that means that they're very porous and permeable and crumbly, and that means that they're really good reservoirs for water and other fluids. In combination with the presence or absence of a matrix or cement, we can classify the sandstone based on the most common grain size, shape, sorting, texture, and composition of the framework grains within the rock. First, we need to try and figure out exactly what minerals our framework grains are made of. The dominant mineral in most sandstones is the resistant mineral quartz, with lesser amounts of feldspar and then tiny amounts of things like titanite, rutile, corundum and zircon, and that's because these are the most resistant and stable minerals in the conditions of the Earth's surface. You can also have some unusual and exotic grains in sandstones. In some rare places on Earth, such as certain beaches in Namibia, diamonds can make up a small fraction of the sand. On volcanic islands like Hawaii or Iceland, the sand can be made of igneous minerals like pyroxene and olivine, and that means that the sand is green and black. These exotic sand types rarely survive long enough to form sandstones because the igneous and metamorphic minerals are easily weathered on the Earth's surface. It's cold, it's wet, there's oxygen everywhere, it's people. You can understand why they don't want to be here. Those minerals then break down and turn into things like clay, quartz, oxides, carbonates. The abundance of quartz compared to other minerals helps us classify the sandstone using schemes such as this really common one by Pettyjohn from 1975. You can find the link in the description. A sandstone that's dominated by quartz framework grains is a quartz arenite, while a sandstone that's dominated by feldspars is an arkose. When we talk about framework grains, we're normally talking about grains that are a single crystal of a particular mineral like quartz. If we observe sand grains that are made of multiple crystals, either of the same mineral or different minerals, or of a completely different rock type, then we call these lithic fragments. They sound really exciting when you say it like that, doesn't it? Sounds like the sort of thing Gandalf would go looking for. The lithic fragments. You'll have to use your hand lens and standard mineral ID techniques to figure out the composition of your sandstone, but try not to get too caught up with trying to find the correct grain composition of every single grain. There's always some interpretive side to this kind of geology, so you just need to be close enough if you're doing it just for fun. Close enough, no, in the ballpark, no, in the same postcode, right? If you don't identify every single grain, the sedimentary police aren't going to come and arrest you and send you to sedimentary prison. This Proterozoic example is mostly quartz, some feldspar, zircon, and lumps of clay and rare grains of chert. So we can class this sandstone as a sublith arenite using the Pettyjohn scheme. You may have noticed this term greywacke in between sandstones and mudstones on the Pettyjohn scale, and yeah, it is pronounced greywacke. And this is an older term for very muddy sandstones. I'll talk about them more later, but they could probably do with their own episode, so I'm not going to go into detail here. Clastic rocks exist on a spectrum from the finest grained mudstones to the coarsest grained conglomerates, and we'll look at mudstones and siltstones and conglomerates in a separate episode and just focus on the sandstones today because that's enough, alright? When we want to be super accurate with grain sizes, like when I'm doing my research, we use something called the phi scale, and we use grain size charts and even microscopes with special software and equipment attached to them, so we can make super accurate measurements and counts of grain sizes and be really, really pedantic about it, because there are people who are really into that kind of thing. I'm not shaming them or anything, I'm not judging, I'm just saying that those people exist. Make of that what you will. This chart shows you the range of sizes and the names of the different grains. I've put a link to it down below so you can go and look at it at your own leisure, if that's your thing, might be. But if you're in the field and you just want a quick guide and you don't want to mess around with grain size charts and phi scales, then you can think of it like this. Fine sand grains are going to be difficult to see with the naked eye, but you can probably make them out with your hand lens. You'll be able to feel them with your fingertips if you're not wearing gloves, and you'll definitely be able to feel them if you rub the rock gently on your teeth. And if you lick it, it'll probably be like a sticky texture there. Just do that gently, you don't have to take a big gobful and then grind your teeth away down to little pegs. This Jurassic example here is a really typical fine grained sandstone. Barely see the sand grains at this scale. They're definitely there. Medium sand grains can usually be seen with the naked eye, especially if there's good lighting and not much matrix, and super easy to see with your hand lens. Definitely be able to feel them with your fingers, and you really don't need to rub them on your teeth. You can see them and feel them. It's fine. I mean, there's probably going to be someone out there who's going to try chewing a medium grain sandstone, and RIP your teeth. This Devonian example is pretty typical medium grained sandstone. Look at the medium grainedness of it. You can see the grains. Coarse sand grains, super easy to see with the naked eye. And if you look at them with a hand lens, especially if it's a rock with not much matrix or cement, you might be able to see features on the surface of those grains, like abrasion marks and pits and dents where they were getting transported before final deposition. And you definitely do not need to test them with your teeth, and you'll definitely be able to feel them with your fingers. Once you pass the granule size, it's better to think of the framework grains as being clasts, because these are usually just chunks of multi-mineral rocks, not into huge individual crystals. When we get things that are this big, we stop calling it a sandstone and we start calling it a conglomerate. So after granules, you get pebbles and gravel, and you know what pebbles and gravel are probably, and that would be a pebble or gravel conglomerate. Next size after that is cobbles. You get a cobble conglomerate, and then once you get up to the size of boulders, especially large boulders the size of small boulders, you get into boulder conglomerates. A conglomerate where there are lots of different lithologies, different types of rock that make up all of the different clasts, are called polymictic. But if all of the clasts are the same, then it's called monomictic. In these Devonian examples from the Isle of Arran in Scotland, you can see that this one is polymictic. There's lots of different bits of types of rock that make up these clasts. But then this other one from the same unit is monomictic. It's pretty much all just made of these chunks of vein quartz. As well as helping us classify the rock, grain size is important because it tells us about the energy level of the depositional environment. Think of it like this: how much energy do you think it takes to move a small boulder the size of a large boulder compared to something like a fine sand grain? A fine sand grain can be moved by the wind or just by you blowing on it because you're bored on the beach. On the other hand, if the wind is strong enough to be moving boulders about, you're in trouble, or possibly on another planet. Our next important attribute that we need to take notice of is grain shape. Grain shape is important because, like size, it can tell us about the energy levels of the deposition environment and about how far and for how long the clasts in the rock have travelled. We describe grain shape using the terms rounded, sub-rounded, subangular, or angular. You can also add words like very or well to the shape descriptions if you like, and you want to be really specific about different layers. So you could say like well-rounded or very angular. But generally it's best not to overthink the grain shape, and I found that the 4 basic descriptions of rounded to angular are good enough for most rocks. Besides, without a microscope and thin sections, you'll be limited to how well you can see the shape of any grains below granule size, especially if it's a very heavily cemented or a very matrix-rich sandstone. In general, grains that are more rounded have undergone more transport in a persistently higher energy environment, whereas grains that are more angular tend to have usually experienced less transport in only intermittently high energy environments. There are always rare oddities that don't quite fit in, like flat pebble conglomerates. Grain sorting describes how similar the size and shape of the framework grains are. A well-sorted sandstone will have framework grains that are mostly the same size and shape. A poorly sorted sandstone will have grains that are very different sizes and shapes. It's not a judgment, it's just a description, so don't get too excited. The sorting of grain tells us about the average energy level of the depositional environment and about the frequency of the different energy levels. A sandstone formed on a beach will generally be moderately to well sorted because the constant action of wind, waves and tides will physically sort the different sizes of grains over time. If you don't believe me, then go and look at how the sizes of sand grains are distributed between the high and the low tide lines the next time you visit a beach. However, beaches often have lots of living things on and in the sand, like crabs, worms, people, the usual, seagulls, gooses. These organisms cause vertical and lateral mixing of the sediment by digging burrows, poking about looking for food, making sandcastles, trying to bury family members who are really annoying. When living organisms churn up and mix the sediment like this, it's called bioturbation. Sandstones formed in high deserts like the Sahara are often very well sorted and have almost spherical grains because thousands of years of constant wind have rolled the grains backwards and forwards, winnowed away all of this finer material, and because the water flow is too low and infrequent to carry larger clasts and pile them up. There's also fewer living things in high deserts compared to the area relative to places like beaches, so there's much less bioturbation. So next we use the information that we've collected so far to interpret the textural and compositional maturity of the sandstone. And understanding the maturity will tell us about the depositional environments of the rock and the history of the grains that compose that rock. So for example, a sandstone with more than 95% quartz framework grains that has no matrix, and where the framework grains are grain supported, the grains hold each other up, that where they're very well sorted and very well rounded, would be described as both compositionally and texturally mature. This means the grains that form the sandstone have been eroded, deposited, lithified, re-eroded, redeposited, re-lithified and transported many times over, often over very long distances. And that leads to the removal of all of those less resistant, easily weatherable volcanic and metamorphic grains and the rounding of any surviving grains. The sand of the Sahara Desert is an example of a modern sand that is texturally and compositionally mature. It's been recycled many times over, with some of it originally being deposited as sand that was eroded from granites over 2 billion years ago. Pretty old that, pretty old. So texturally and compositionally mature sandstones often turn out to have been deposited in ancient deserts, but not always, so be careful with your interpretations. A sandstone with lots of clay matrix, framework grains that are 50-50 between quartz and then feldspars and other less resistant grains that are matrix supported where the grains aren't touching because there's so much matrix it's forcing them apart, where the grains are poorly sorted and very angular, would be considered both compositionally and texturally immature. This means the grains that form the sandstones have been transported relatively quickly and over relatively short distances between the original point of erosion and the place of final deposition. Burial at the deposition site is usually also quite fast for immature sandstones, so there's no chance for the grains to be sorted and reworked and rounded before final burial, say for example on the seabed. Grey wacky sandstones are often immature because they form in areas where there's lots of tectonic activity from the rapid uplift of land relatively close to a depositional basin, such as when continents collide. The uplift of land results in a lot of erosion of bedrock to produce clastic sediments with relatively short transport times. Tectonic activity during uplift, like earthquakes, often causes turbidites, which are like underwater avalanches, and these commonly form grey wax. During the turbidite event, the sediment is jumbled up and mixed and then deposited and buried very quickly, so there can be no further sorting or rounding of the grains on the seabed. So it turns out that sandstones with these characteristics are often deposited in ancient turbidite events, but not always. Be aware that these are just two examples of the extremes of the maturity scale. There are other depositional systems that can produce these features, so you have to collect and compare all of the evidence before you make an interpretation about the depositional processes and environment of a particular sandstone. That goes for any rock really. This sandstone is an example of how you can get it wrong. In my PhD thesis, I originally classified it as a rounded to moderately sorted, medium-grained, class-supported lithic arkose. Later, I realised it was actually a muddy limestone where the carbonate minerals had been replaced by silica during weathering at the surface, and that the rounded quartz sand grains were silicified carbonate grains called ooids, as well as fossil algae in shells. I then incorrectly interpreted the depositional setting as a beach, when it was in fact a shallow marine offshore carbonate platform, and that in turn completely changed my interpretation of the depositional setting and the environments across the basin, which was about 500 kilometres wide. But that's okay, you learn by getting things wrong and doing it and trying again. I still got my PhD, and I'll always remember to check for those features that indicate silica replacement of carbonates in the future. Lesson learned. Now we've gone over the basics, let's have a go at classifying some sandstones. I'll show you an example and then I'll give you some to practice on your own. I'm so generous. So this sandstone example has very little matrix but has a pervasive silica cement. It's very heavily silica cemented. The framework grains are mostly quartz, but there is abundant feldspar too and an unusually high amount of minerals like magnetite, titanite and zircon. There are small lithic fragments of clay and larger lithic fragments made of mudstone held together by microbial mat. There are also some rare fragments of red jasper-like chert. Looks like it's been much more rounded than the other grains in the rock. So we could classify this rock as a grain-supported lithic arkose with moderately sorted subangular grains. This sandstone is both texturally and compositionally immature, as it's from a 3.2 billion year old Moody's group from South Africa. This was one of the first ever sandstones to be deposited on Earth. The grains were eroded from volcanic rocks, cherts and iron formations that were only slightly older than the sandstone itself, and they were deposited in an area of rapid uplift that was close to the final deposition site. The grains didn't have to travel very far and did not have time to be recycled, rounded, sorted and reworked. Also, the atmosphere had very little oxygen back then, so less resistant grains could survive longer, which is why we find grains like magnetite, pyrite and even uraninite in these sandstones. Pause the video at each example and write down how you would classify each sandstone. I'll put my interpretations at the end of the video. Don't worry though, I haven't put any surprise trick sandstones here that are really silicified carbonates or anything weird like that. These are all pretty standard, normal sandstones. Learning how to classify sandstones is just one tool that will help you to interpret and understand the ancient environments recorded by clastic sedimentary rocks. Other tools are things like the presence or absence of sedimentary structures and fossils. The wider geological context is also very important too, so what kind of rocks are above and below your sandstone or next to it? What type of basin was it deposited in? Where in the basin is your sandstone? Finally, if like me you're doing geology as your job or as part of a degree, you can use advanced techniques like different types of microscopy and geochemical methods to pull out information that can't be seen with the naked eye. But we need to put all of this evidence together before we can really try to interpret ancient sedimentary environments. And even when we have all that evidence, there may still be multiple possible answers. So it's up to you to decide which interpretation best fits the rocks that you're looking at. So remember, you fit your interpretation to the data that you observe and the actual rock samples. You don't try and fit the rock samples to what you want them to be or what you want them to represent. So there you go, an extremely quick and basic guide to the what, why, how and where of sandstones. I hope you enjoyed that video and found it useful. Have you seen any cool sandstones recently? Would you like me to go over some of the more advanced topics like sedimentary structures and how to interpret depositional environments? Do you have a request for a topic you'd like me to cover in a future video? Let me know in the comments below, just in case you didn't know where they are. Until then, have fun with your rocks, stay safe, and I'll see you next time. Later potatoes. Bye bye. What is a sandstone? Where is a sandstone? How is a sandstone? Exaggerated hand movements. Todger. I'll never know. Let me know in the comments below. Oh, look, I'm being dynamic. Comments below. Energy.